Right, I'd like to introduce Shane Nanayakarra, if I got that right. Shane is a cardiologist at the Alfred Hospital with obviously research interests in cardiology things. He's going to talk to us about some machine learning that was part of a project we did with the Datathon. It wasn't Sydney, wasn't it?
Yeah, that's right. Great. So, hi everyone. While the talk is coming up, there's a couple of things I want to say. The first is I feel like a fraud because I'm a cardiology person in an ICU conference and it's very scary. The things that I like, that cardiology and ICU both share big data sets, which is kind of nice. But we went to one of our big cardiology data sets recently before this started, and I came to Dave and I said, I've got this great big data set, it's 35,000 patients, this is fantastic. And then Dave said, we've got this Datathon with 1.5 million patients. And then I just went home and cried, frankly, and that's why I joined. I'd like to thank every ICU that contributes to it, because I think it's an amazing project. I wish cardiology had something similar. And as Peter said, I went to a Datathon in Melbourne and Sydney, and there was one I know in Bendigo recently as well, and they've been really good at kind of starting this project. So thanks for having me as a fraud. All right, so can I go forward with this one? Or do I need you to do that? All right, great. Can you just go full screen with it? I have a Mac, and so that was the first half an hour of the presentation. Is just go view, full screen. Yeah, Control L. Perfect, and then just page up, down. So page down there. So this project was looking at cardiac arrest. And so the idea was that could we do better at predicting cardiac arrest? I've always been fascinated, obviously, by cardiac arrest being the join often between ICU and cardiology, but we're very bad at predicting mortality often and predicting lots of things. I initially started with looking at neurological outcome, but I know this data set would be more useful to look at cardiac arrest. I have an interest in artificial intelligence and machine learning, and I'll talk more about what those really mean, but they're basically a really good way to do predictions. And so I wanted to see, could we improve the way we predict outcomes after cardiac arrest using the ANZICS dataset. This is looking at, from the recent AHA statistics, talking about cardiac arrest, and generally the outcomes are dismal. But the more important point to me is that there is variation. There are people that surprise us constantly, people who do very well, who we discount, and people who don't do so well, where we predicted that they would do well. Next, please. There have been previous attempts at predicting outcomes after cardiac arrest, and people have used scores, either scores that have been developed within the confines of a particular data set related to cardiac arrest, or using existing critical care scores. But all of them highlight the same thing, that they're either modest predictors of illness severity, or next please, or that they're kind of moderate, getting better, but with some fluffy language. And then the next one, again, using existing scores that it didn't predict mortality. I'd like to highlight that next bit, though, that the amount of time before CPR, that the low flow interval and the absence of initial ventricular arrhythmia were independently associated with mortality. And if you go to the next slide, these things are really useful in cardiac arrest. And these things don't necessarily exist in ANZICS. We don't necessarily know their rhythm at admission, their time to return to spontaneous circulation, whether they had the presence of bystander CPR, time for the ambulance to arrive, time of adrenaline, and overall how long their CPR was. They're useful, but they can sometimes be hard to collect, particularly at the bedside, depending on how good your ambulance service is, what the documentation's like, how quickly that comes to the ICU. Your ability to prognosticate at the time the patient arrives can be variable. So going to the next slide. I wanted to bring machine learning into this and see whether these techniques could help. This was in 1987, and I find this an interesting quote because I think it's been repeated every year, even up to this year, where people say that after hearing for several decades that computers will be able to assist with difficult diagnoses, the practicing physician may well wonder why the revolution hasn't occurred. And they wrote this, and they wrote this whole article like it was about to happen that year, but for years we've been joking about it, but now we're going to be serious. But we still have this issue that we haven't really had computers take over our jobs as such. The next one, please. I'd like to highlight what machine learning is. Essentially what we do currently is we get data points, it doesn't matter what the X and Y axis is, and we build a model, a maths model, logistic regression or linear regression are just those things, trying to put the Y and the X together on some kind of model and see how well you can fit the data. Machine learning is kind of the opposite. You put the data in and then it gives you the algorithm that was able to to match all of that. The important thing about machine learning is it doesn't have to fit a particular model, and even more importantly, but more concerningly, is it's sometimes something that we don't understand. And so where logistic regression or linear regression are things we've heard about, and you can kind of look and go, oh, this was this coefficient or this coefficient, we can kind of get it, it's just maths. Machine learning can be a little bit scary because it's great at its accuracy, but if we don't understand how it works, then how can we trust it? And so it's been used in lots of areas. It's been used for things like self-driving. This is Tesla, the car company from the United States. You can see on the right-hand side it has cameras all around the car, and it's analysing what each of those objects are, it's understanding what those objects are, and then driving the car around it. But we don't 100% know it understands what it's doing, because every now and then there'll be an accident where it hits a person because it recognised the person as the wrong thing. Now, it does that with a greater degree of accuracy than human drivers, where a machine seems to be more accurate and has less accidents than a human driver. But we still don't understand why. This is an example of people using machine learning, but for economic analysis. So this is putting a street camera on a highway and then looking at every car and then using machine learning to determine what the model of the car is, what year, what make, and even understanding to some extent what the number plates are, and then figuring out on the next slide what the average income would be for an area based on what kind of cars they are. If you drive expensive cars, then you must be in a rich area, and if you have less expensive cars, perhaps you're not. What's interesting is when they created this map on the next slide, they correlated with crime reasonably well, and they're saying that maybe you can make these predictions, but these are big steps to make. Next. So there's this trade-off. We have these algorithms on the bottom right, things that we understand that have less predictive capability, but they make sense. And at the top left, we have algorithms, and probably the most famous one is deep learning, where we don't really understand how it works completely, but it's very good at predictions. And we have this middle ground that we're trying to meet. What we tried to do in this project is have those deep learning models, or models that can do predictions well, but then next is we tried to make them meet by adding explainer models on top. And this is where it's coming to in medicine, is that we have regression methods and we have machine learning methods, but really we're trying to come to this same middle ground overall. If you go on to the next one, please. This is where people have said the pathways for machine learning and artificial intelligence in medicine overall, and particularly because we're going to have a lot more data. It's not just things like ANZICS. It's going to be the electronic health record. It's going to be people having things like Apple Watches and Fitbits feeding into their health data. It'll be proteomics and genomic data that comes into it. And you might have seen recently there was a paper talking about genetic data predicting heart attacks in people with reasonable accuracy from this week. So this idea that we can get to using, when you have this much data, you can't rely on standard mathematical models anymore. So this is from a machine learning person, and this is probably a really good summary to think, when can you use machine learning? Machine learning can't think. It's not actually intelligent. It's just making a very good maths model that we don't understand, but it's not going to replace us because it can't be creative, it can't be emotive. Sometimes that's good and sometimes that's bad. But if you can think of a job that you would do that takes less than a second to think about, so something that wasn't really requiring your thinking in the first place, that's probably something a machine will do. So calculations are something a machine will do. Anything that's fairly automatic is something that machine learning will be capable of, like looking at a car and determining what brand it is. People have used it in skin cancers, and basically you take a photo of a particular lesion with your phone, and they've shown that, this is published in Nature, that you can be fairly accurate as a dermatologist to determine whether something's melanoma or BCC or SCC or otherwise. And people have used it just recently in the last few months to look at retinal disease, whether you can predict diabetic retinopathy, for example, from a data set. And they used over 500,000 images from people's eyes from the UK. What was interesting is they were good at picking retinal disease, as good as an ophthalmologist. But more scarily, they were also good at picking gender, or whether the patient had smoked, or what the ages of the patient was within about 3 years. The advantage is that they were good at doing this. The big advantage is if you're in a third world country, you can take an algorithm there. You can't take 20 ophthalmologists there, but you can take an algorithm there and potentially bring a lot of accuracy to places that didn't have it before. We'll go to the next one, that's fine, thank you. The big problem is bias. If I take a machine and I get it to learn from data, and I give it data from 1,000 white people, when I take it to a black person, it will be wrong. And similarly, if I take it from Asian people or Australian people, whatever it is, if the data that it's learnt from is not the data that you're going to test it on, then it will make mistakes. And if you don't understand what the machine's doing in the first place, then you can't trust it. And this is where the fear comes around. machines can be biased and the big fear is that you don't understand when they're biased. An example in the United States is the police force tried to use an algorithm to predict whether someone would re-offend. After they leave prison, would they commit a crime again? And it was very biased against black people, partly because of the data it was trained on and the state that it was trained on when they took it from a southern state to New York. And we need to understand this in medicine. I'll come to what we did. We took 1.5 million patients from the ANZICS dataset that had cardiac arrest. We excluded people who were electively admitted. It was very interesting to find people who were electively admitted with a cardiac arrest. Inter-hospital transfers were taken out. People with any treatment limitations were taken out, and anyone with unknown mortality. So we ended up with about 40,000 people. This is generally the cohort. There's about a 50% mortality. On the left-hand side, you have the survivors, and the right-hand side, you have the non-survivors. You can see the non-survivors are slightly older. There's a slightly greater predominance of males in the survivors. And the temperature, which has been published recently, is kind of interesting, but the temperature is slightly lower in the non-survivors. But interestingly, their creatinine was very different. This is, as you may be familiar with the ANZICS dataset, the comparison of the highest and lowest worst values, so the best and worst values, in the first 24 hours. Then we compared machine learning models. Most of these words may not mean anything to most people. I'm going to quickly describe what a few of them are because it will be important. And I think in the next 10 years, these will become as familiar to you as things like logistic and linear regression. They are important things. A decision tree is really basic. It takes a person, divides them into two groups. Are you under 65, over 65? Then it takes that under 65 group and says, is your creatinine this or that? And then it keeps going and going and going until it makes a prediction. A random forest is if you had a group of trees. It's very well named that way. So if you take a bunch of those trees and make a forest out of them, so you have hundreds and thousands of those trees, then you can make a better model out of it. An ensemble method a little bit further down, that one is where you just combine a bunch of these models together. The other one I'm going to mention is a neural network. A neural network is the one you'll hear most about. This is the one that makes cars drive themselves, and this is the one that will be the focus of most attention going forward. It's the one that's least well understood. And if you take a bunch of neural networks, you get something called deep learning, where one network teaches the next network, which teaches the next network. This is how the models performed in this particular data set of cardiac arrest, which is a notoriously difficult area. Across the x-axis, you'll see different models we applied. On the far left, to the left of the red line, is actual mortality, 46%. Apache score, ANZROD. Logistic regression, the artificial neural network, a random forest, a support vector classifier, and right at the end, an ensemble, which is a mix of all of those models, and something called a graded booster machine. The name of the models isn't so important, but you can see that accuracy varies significantly between the models. More importantly, it's not just necessarily what the actual prediction was, but on the next slide, things like the area under the curve, which is probably our most important comparator. The y-axis is slightly skewed here, but the Apache would be accurate to around 0.8, and we can see that our logistic regression, 0.82, and on the far right are our machine learning models, again, being a little bit more specific. This is, again, just a comparison of all of those things. There's the area under the curve in that middle column, the predicted mortality on that left column, and the other ones on the right-hand side are talking a little bit about how accurate the model is, and importantly, things around misclassification. I'll skip over that horribly blurred slide. This slide is really important to me, and it was a bit of frustration for a while. In green are people who survived, and in red are people who died, and the x-axis represents what your score was for any particular model. So for Apache 3, if you're on the left, you can see your score was low, you had a chance of surviving, and on the right, for the red people, you can see as your score was high, you had a higher chance of death. But the important part there is the amount of overlap. There is a significant group of people who have a high score for Apache 3 who still survived. And similarly, there's people who have a low score in the dead category who clearly died. And so it's wrong. There's a misclassification a significant amount of the time. And the more you can get rid of that overlap, the more we would trust a particular algorithm, because if it gives you a low score, you want to be fairly confident the patient will die or live. ANZROD, you can see overlap there. And on the next slide, this is comparing what those machine learning models do. This is logistic regression on the top, so fairly similar to something like ANZROD, as you'd expect. That's a similar kind of model. And a machine learning model on the bottom, where it's a little bit more separated in terms of those curves, and you have less of that overlap. We'll skip over this for the moment. So we looked at how, when it gives these predictions, that's all well and good, but how can it explain it? This model called Lyme, the acronym doesn't matter, is a way of explaining. And what it does is it takes your data, takes some people, so in our case, takes some patients, changes their numbers a little bit, and then sees what the model does. Then it'll change them again and see what the model does. So if you can't read the coefficients, if you can't look at a model, then what it'll do is it'll keep changing the data and understand how it's making predictions, and then it'll tell you, this is why I think the model chose this particular patient to die or this particular patient to live. In this case, it's trying to understand that picture of a frog, and it's telling you, I think it's a frog because in the first picture, it has that kind of appearance, this kind of eyes up the top and this mouth kind of thing going on, and then it thinks it's billiard balls in the second one, but it only gives it a low rating of 7% because it's got that round thing up the top right. And it thinks it's a balloon on the far right one because it's got that patch of red, and I've seen that patch of red in a lot of pictures before. Or it's been used for algorithms for recommendation. I think this is a good food review that you've left on Deliveroo because they use the word, or bad review, because they've used the words tasteless and burned. Or for service, they've said the words fastest delivery times. And every time I've read that, that's been associated with a good review. It was quite funny. As I was coming up here onto stage, I saw Netflix gave a recommendation, and it said Gossip Girl, which is horrifying for me because I don't know how to feel about that. I'm sure it's the algorithm's wrong. All right, next. This is an example, and I apologise for the blur, but this is an example of where we applied the model to see why it thinks this patient lived or died. So this is someone who was given a high chance of survival, 83% chance of survival, and they actually did live. So it thinks they lived because their GCS was good, they were oriented, they didn't have chronic respiratory disease, their lowest temperature was above 35, and their highest creatinine was less than 85. So it thinks they're all positive things. But it said the things that increase their chance of death, the reason it didn't give it 100% was because their heart rate, their lowest heart rate never got below 75. Their lowest respiratory rate never got below 15. And then it talks about their highest heart rate in a very small area. So you can see why it's making that decision. On the next one, this is someone who actually died, someone who was given a chance of 27%, and it says that. It thinks that they were going to die because their GCS motor had no response, their urine output was very low, their verbal response was unresponsive. But the things that were in their favour, the absence of chronic respiratory disease, that they actually did have a low heart rate, they got below 52, they weren't tachycardic the whole time, and that their white cells never got that high, and it's seen that being a bad predictor overall. But the next one is most interesting for me. This is one where it was wrong. So it gave it a 78% chance of survival, but the patient died. And this bit here is what I'm most interested in. If we can't understand models, can we trust them? It needs to explain what the mistakes are. So this is one where the patient died, despite the fact the model thought they were going to live because they obeyed commands, they were oriented, they didn't have chronic respiratory disease, they didn't have liver failure. They did have a really high creatinine, and maybe the model didn't put enough emphasis on the fact that if your creatinine gets to 170 in 24 hours, that was a bad thing. Or that they were tachycardic, or that they were tachypneic. And maybe like a lot of interns who don't put an emphasis on tachypnea, that is a really important thing. Importantly, the model can only explain to you whether a patient's going to live or die based on the things that you gave you. So it doesn't know anything about ROSC. It doesn't know what the initial rhythm was. It doesn't know whether there was bystander CPR. They were probably really important things, but it can only know the data you've given it. So it'll only make its explanations based on what you've given it. So to conclude, I think these models have a really great way to be able to advance on some existing critical care models, particularly because we're getting these massive data sets where you can extend beyond logistic regression or linear regression techniques. But the real trick is that they can add explainability to get rid of bias, and explainability to improve our trust in what they're going to be able to do. And in the future, but not yet, explainability around treatment decisions, whether if I do this or if I do this, can you show me 500 patients in the data set who've done this before and how it worked out for them? Thanks very much for your time. Thank you.
Any questions for Shane?
Hi.
What kind of data sets, what size data sets do you need? Do they have to be enormous?
No, they don't. It depends. Everyone's size depends on the quality of the data. The big thing is the balance between basically how many rows do you have and how many columns do you have. If you have 20 patients but you have 400 different variables, then it's not going to work very well. So it's that balance between the two. And the other thing is it depends on the algorithm. If you're doing deep learning, which is the most sexy one, then you do need really a lot of data. That's something where 1 million patients is great. But if you're doing some of the other models, you can actually work with less data. So I would generally say something like 500,000 patients at at least. If you're doing on 30, 40, 50 patients, it's not going to work out. In those situations, standard stats will beat a machine learning model any day of the week. But in those bigger data sets where you're getting a couple of hundred, thousands of patients, these things can be useful. I didn't talk about one area of machine learning which is called unsupervised machine learning. That means you give it a data set and then you ask it to find subgroups basically within your data set. I think that's got a real future for something like most of what we do. It's what I said at the start with cardiac arrest. You have cardiac arrest patients who do well, those who do badly, and those somewhere in the middle. And there probably are clusters under that we find out. And the best thing I can compare to is cancer. When we found out about breast cancer, it was probably, it's bad and it's just universally bad. And then you find that there are subgroups related to hormonal receptor presentation or genetics. And the more we find those things, then the better we can treat our patient groups. Sasha.
Great talk. What sort of percentage of poor outcome would you be happy with one of these machine learning programs to say we should stop now, we shouldn't waste 100 hours or 72 hours to assess an outcome?
Yeah, I think it's a really bad idea for these things to make any decisions because they're not smart and they're like what I was saying about the end where they only know what you've given them. They'll say something wrong. And I think of it very much like an intern who's confident or not confident. That those curves that I said where there's a low score and a high score, the closer those two things are together, the more I think a model is not confident. Where if I ask the intern what's the chance of death and they say 55%, I don't know what to do with that number. And I would say most clinicians, that's a useless algorithm if it keeps saying 55 all the time. But if it keeps saying 0 to 10 or 90 to 100, that's more useful. But to a clinician, I don't want it to tell me now you should turn off the machine. I want it to say this is the reason it's high, this is why I think it's high, and now you make the decision.
Last question. Within cardiology, what are you interested in doing with the machine learning?
Lots of stuff. I think there's a couple of big areas of machine learning. One is just looking at numbers. One is looking at text. The big area I think is interesting is imaging. So it'd be really cool to think you could do an echo. It could understand what a 2-chamber view and a 4-chamber view and 3-chamber is. Then it could give you maybe an EF and things. But more importantly, maybe it could make some diagnoses. There's been some work overseas where you could pick amyloidosis as opposed to just left ventricular hypertrophy from hypertension by looking at thousands of these images. And that'd be amazing to do for like the third world. Because if we could just train it on a whole bunch of data sets here, and then you could go and do an echo somewhere else, and then it would give you, cardiologist level predictions like what happened with dermatology and with ophthalmology, I think that'd be really nice. But I'm really mindful of the bias. If it, again, you take an echo here and you go to Fiji or you go to South Sudan, they're very different humans, and so therefore you could be afflicted with bias.
Any other last questions?
It's good to talk about linking data sets and databases. Is there a cardiac arrest registry that patients with APD see some of these things?
Yes. So, I think the more you link these things, the better. Because as I was saying about the explainability, if you don't know all the data, then that's a dangerous thing. It'll make bad predictions. I think linkage is huge. At the Bendigo Datathon, there was some really great work where it's been linked with things like the National Death Index, but also with government-level data around hospital admissions. I think that's really useful. Things like the ambulance data set will also be really interesting. So I think the more we link with all of these databases, then you get this really comprehensive understanding of a patient and their journey. I think a great example of this is Google did one with thousands of electronic medical health records, and then it trained it to read text. And so we're saying predict mortality, but then explain to me why. And it would say things like, this patient has a pleural effusion, but they also had breast cancer. Maybe the breast cancer was malignant, and that's why they had a pleural effusion, and maybe that's why they did badly. And it can only understand that because it could read the whole record. I think that kind of stuff will be really important with linkage. We've got all these big data sets in silos. The more they come together and the more people get knowledge about machine learning, I think it'll be really powerful.
I'm not sure that answered your question. Was it about whether we should have linked it or not? We should. Yeah. Okay. Cool. Thank you very much. And thank you for other presenters and for coming to help us present. Thank you.